In today's video, we're going to look at the law of sines. This works for any triangle. So before, we have looked at just right triangles. Now we are looking at oblique triangles. So they are triangles with no right angles. Okay. This does also work for right triangles. It's just that we have other methods for completely solving a right triangle for all sides and angles. So we don't tend to use this for right triangles, but this does work for any triangle that you see. There are two types of oblique triangles. There's acute and obtuse. Okay? Acute triangles are just ones where every single angle in the triangle is less than 90 degrees. An obtuse triangle is going to have at least one angle in it that is greater than 90 degrees. It can't actually have more than one angle greater than 90 degrees, or the angles would add up to more than 180. But an obtuse triangle will have at least one angle that is greater than 90 degrees. I'm going to show you what the law of sines is relevant to an acute triangle. Okay, it's just easier to solve that way. There is a proof in the textbook to show that it also works for right triangles and for obtuse triangles, but I'm just going to show you for an acute triangle as it all kind of follows the same way. Let's say that I've got this triangle here. Okay. And I've got sides A, B, and C. And I've got alpha, gamma, and beta as my angles. Okay, and I'm going to call the vertices of this triangle A, B, and C. Now, because we are not looking at right triangles anymore, we don't have a hypotenuse. Okay, so normal trig functions as we've used them previously don't work. Okay, we've got to find another way to use those trig functions. The way that I'm going to prove this is actually by going back to what we do know. Okay, I'm going to call this H. Okay, I have two right angles here and here. Okay, so I've just joined C to its opposite corner. Now, using what we know about trig already, I can say that sine of alpha, okay, using what we know about right triangles, sine of the angle was opposite over hypotenuse. Okay. Well, the opposite side to alpha, when I've drawn in this H, is H. And then the hypotenuse for this right triangle would be B. So I've just taken this to be a right triangle. Okay. That tells me that I can rearrange this and write H as B times sine of alpha. Alternatively, I could have taken this as my right triangle. Okay. And now I can write sine of beta is equal to, again, opposite divided by hypotenuse, H over A. So H can also be written as A sine beta. So I can set these two things equal to one another. And I know that A times sine of beta is equal to B times sine of alpha. Okay. So I can also rewrite this and say that sine of alpha divided by A would equal sine of beta divided by B. Okay. If I would have done this slightly differently, and instead, if I would have joined A with its opposite angle and called this H, where I had two right angles here and here, and done the same thing, if I would have done that, I would have found the same thing but with gamma and beta. So I would have found that sine of beta over B would equal sine of gamma over C. This is the law of sines. Okay. Sine of an angle divided by the length of the side that's opposite that angle is equal for every single one of our angles and sides. So sine of alpha divided by the length of the side that is opposite that angle is equal to sine of beta divided by b, where b is the length of the side that is opposite the angle beta, and same with gamma and c. So it works for all of our angles and all of our sides. Like I said, I've done this for a triangle where each of the angles are acute. So each of my angles is less than 90 degrees. Alpha, beta, and gamma are all less than 90 degrees. It also works for obtuse triangles where we've got one angle that is greater than 90 degrees, and it works for right triangles where you do have that 90-degree angle in there. The proof for those is on page 484 of the textbook if you are interested, but it does follow pretty similarly to this. We want to look at solving some triangles using this method. Okay. There's different types of triangles. We're mainly going to stick with two of the three types of triangles that you are going to use the law of sines to solve today, and then in the next video we will look more at that third type of triangle that you will solve. But the first two types of triangles are known as SAA and ASA triangles. What does that mean? It means that given a triangle, I'll draw out the same triangle that I had before. So we have alpha, beta, gamma, A, B, and C. Okay. For side angle is what SSA stands for. You are given two angles and a side that is not between the two angles. So let's say you were given the angle alpha and the angle beta. You would also be given the length of the side A or the length of the side B. You would not be given the length of the side C, because C lies between the two angles that you have been given. Okay, so side angle SAA triangles, they are the triangles where you are given two angles and then one of the sides that does not land between the two angles. So it's going to land opposite one of those two angles. Okay, it is not going to be the side that's between them. An angle side angle triangle, so ASA triangle. Okay, again we've got alpha, beta, gamma, A, B, and C. This time you are given two angles and you are given the side that is between the two angles that you are given. Okay, so you have the two angles and the side that is between the two. Okay, so in the first one you're given two angles and a side that doesn't lie between the two of them, and in the second type of example you are given two angles with the side that lands between them. These are the first types of triangles that we are going to use the law of sines to solve. So in my first example, okay, and again, when it says to solve the triangle, we are solving all sides, all angles. Okay, so we want to solve the following triangle. So I am given that this angle is 43 degrees. This angle is 71 degrees. This angle I do not know. I'm going to call it gamma. I am given the side that is between the two angles, and I don't know either of the other two sides. Okay, I've got to solve for A and B and gamma. Easiest thing to solve first whenever you're given one of these examples, whether it be an SAA or an ASA triangle, you're given 2 out of 3 of the angles. Always solve for that third angle first. It's the easiest thing to solve for. Okay, you know all the angles have to add up to 180, so go ahead and find that third angle first. So I know that 71 plus 43 plus gamma must equal 180 degrees. If you figure that out, that tells me that gamma must be 66 degrees. So that's the easiest thing to figure out first. Now all we need to do is to find A and B, and this is where the law of sines come in. So I know that sine of alpha, or the first angle that I have here that is opposite A, sine of 43 degrees divided by the side that's opposite it, so A, is equal to sine of 71 degrees divided by the side that's opposite that, which is equal to sine of my third angle, which was 66 degrees, divided by the side that is opposite that. Okay. This is where you can plug stuff into your calculator. Remember, we're dealing with triangles, so we're going to be in degrees mode. Whenever we deal with triangles, we're always in degrees. When we deal with the unit circle, 9 times out of 10, we're going to be in radians. But for triangles, we always use degrees. Quickest thing to figure out, and this is the thing that you've got to figure out first, is sine of 66 over 11. Okay. From there, we can kind of figure out some other stuff. So we can figure out A and B using this. So I know sine of 43 degrees divided by A is equal to sine of 66 degrees over 11. The way that I'm going to solve this, I've got to manipulate this. So I know if I multiply both sides by 11 and both sides by A, I get 11 sine 43 degrees is equal to A times sine of 66 degrees. So now if I divide both sides through by sine of 66, I get A is equal to 11 sine 43 divided by sine of 66. Which is equal to 8.21. Okay, I would take most of these to 1 or 2 decimal places, okay, just for accuracy. And you can do the same thing to figure out B. So this time I'm going to set sine of 71 degrees divided by B is equal to sine of 66 over 11, and you're going to manipulate it to find B. So that tells me that B is equal to 11 sine 71 divided by sine of 66. Which equals 11.38. So I found A, I found B, and I found that third angle gamma. So we are completely solved for this triangle. The other type of triangle that we had was where we had the side that was opposite one of those angles, so it wasn't between the two angles. So we had that side angle type of triangle. So we're going to solve one of those this time. And it falls out in pretty much the same way, where first we are going to find that third angle, then we are going to use the law of sines. So in this example, I'm given that this angle is 54 degrees, this angle is 82 degrees, I don't know this angle gamma. B and C I don't know, but I do know that that side is 9. So like we said before, we've got 2 out of 3 of the angles. So the easiest thing to do is go ahead and find that third angle gamma. We know that they add to 180, so that tells me that gamma is equal to 44. Now I use my law of sines. So I know that sine of 82 degrees divided by the side that is opposite it, so 9, and then sine of 54 degrees divided by the side that's opposite it, that's B, is equal to sine of gamma, which was 44 degrees, divided by C. Okay. Now you can manipulate this in the same way that we did the last one. So we're going to set these two fractions equal to one another, multiply both sides by B, multiply both sides by 9. That will get rid of the fractions entirely. And then we can divide through to find what B is. So when you do this, I'll tell you what the answers are. You get that B is going to equal 9 sine 54 degrees divided by sine of 82 degrees, which comes out to 7.35. And C is going to equal 9 sine 44 degrees divided by sine of 82 which comes out to 6.31. So in these examples, we've looked through those two different types of triangles. We've got the side angle angle and the angle side angle triangles. So they're the ones that whenever you get those, you know you can go ahead and use the law of sines. The other type of triangle that you will come across is when you are given two sides and the angle, or one of the angles, that does not land between the two sides. So the only other type of triangle where we are going to use this law of sines is when you are given a triangle like this and you have alpha, beta, and we'll call that gamma, A, B, and C. Okay? You will be given, let's say, A and B, and then one of the two angles, one of these two angles, alpha or beta, that does not land between the two sides. So this is called a side-side angle. So the angle is outside of the two sides. So we are not given gamma. Okay, it could be alpha or beta. Okay, that is the other type of triangle that we are going to use the law of sines for. That's what we're going to look at in the next video, because there are different possibilities for these triangles. There can be cases where there are no possible triangles, and we'll find that from the law of sines. There can be cases when there is only one possible triangle, but there are also cases where we can get two possible triangles out of this. So two different sets of measurements that work using the law of sines. So that's what we're going to look at in our next video.